In this section, we're going to talk about linear models and scatter plots. Let's begin by defining a scatter plot. This is a graph in which a set of data for two variables is charted to determine if a correlation can be made between the two variables. Now, this graph is going to have a bunch of points kind of all over the place. It's scattered, hence the name scatter plots. Now, correlation, this is a relationship between two or more variables, and a positive correlation shows that as one variable x increases, the other variable y increases as well. So one grows and the other one grows. A negative correlation, however, shows that as one variable x increases, the other variable y decreases. So as one grows, the other one kind of shrinks or gets smaller. Here's an example of a set of data. I asked 20 survey participants two questions. How old are you? And how many vehicles have you owned? Now, I didn't stipulate whether the vehicle is new or used, how much it was worth. So this could be people that are buying brand new cars that are, $40,000, $50,000 or something. And it could also be people that are just buying some really cheap cars, maybe like $500, $1,000. They drive it until it breaks, they get rid of it, they get another one. Okay. So let's start. I asked a 17-year-old, and they've owned 0 cars. I've asked an 18-year-old, they owned 1 car. A 20-year-old owned 1 car. A 21-year-old owned 2. A 22-year-old owned 1. Okay, a 24-year-old has owned 2. 25 has owned 2. 27, 3 cars. 28, 1 car. 29, 3 cars. And I've actually got 2 more 29-year-olds. They owned 3 and 4 cars each. 3 30-year-olds were asked. 3, 4, and 4 cars. 32, this person owned 5 cars. 33, this person 3. 36 years old, 6 cars. 37 years old, 5 cars. And 41 years old, they've owned 7 cars. Now again, these are not... This doesn't say that they're, super fancy brand new cars. Doesn't say that they're old cars. It also doesn't say that they own all of these cars currently. It's just the number of cars they have owned at one point. Well, what do we notice about this data? What pieces of information jump out at us? It appears that these ages have pretty low cars owned. 0, 1, 1, 2, 1. And then over here, these are some of my older survey participants, and they've got numbers that are quite a bit larger. 5 here, 6, 5, and 7. So to me, something I notice is that as someone got older, as age increases, it appears as if it's more likely that they've owned more cars, which I think that makes sense, right? When you're 16, 17 years old, you're just starting out driving, you might not have your own car, but as you get to be a young adult, you'll probably need, maybe a car to get around. Maybe that first car is something that wasn't worth a whole lot and breaks down. You get a second one. And then as you get older and older, there are more cars that you may have owned or leased, etc. So let's write that down. It appears as age increases, the number of cars owned increases. Now, this information is great and all. It has everything I need. Has all of my survey participants, has their results, so the ages they are, as well as how many cars they owned. But not everyone looks at a table like this and goes, wow, that data looks really fantastic. I'm pretty sure it might just be some mathematicians like myself. So instead, we can give this same information in a graph. And oftentimes, people might prefer that just because it looks a little bit cleaner, it's a little more intuitive to read. Here's the same information in a graph. And yes, when I graph this, I've got a 17-year-old who's owned 0 cars here. I've got a 20-year-old who's owned 1 over here. I've got some 30-year-olds that have owned 3 and 4. So there's the same information. It appears that, yes, there is a positive correlation between age and cars owned. As age increases, my X, my Y, number of cars owned, also increases. So then, is there something more that we can do with this? A line of best fit or trend line is a straight line that best represents the data on a scatter plot. The line may pass through some of the points, none of the points, or all of the points. And when we do that, we're creating a linear model, which is an approximation for the line of best fit. In other words, I'm going to take this set of points here, the scatter plot, and I'm just going to draw a line through it the best that I can, trying to get as close to kind of the center of all of this data as possible. So here's an example of that. This is called a linear model. Okay, and what I'm going to do with this is I'm going to pick 2 points here that are as close to this model as I can find, or maybe they're exactly on it. Here I've got the point 17.0 and 24.2. They both happen to be pretty much on that line. So with those 2 points, I want to first find the slope, and then once I have the slope, find the full equation of this line. Well, the 2 points I picked, 17.0 and 24.2, let's call this point 1, and let's call 24.2 point 2. Then that makes 17.0 x1, y1. So 17 will be x1, and y1 will be 0. 24.2, this will be 0.2, so this will be x2, y2. So 24 here, and then 2. To find the slope, I use my slope formula. M equals y2 minus y1 over x2 minus x1. So M will be 2 minus 0. And this will be over x2 minus x1 is 24 minus 17. Two minus 0 is 2. And 24 minus 17 is 7. So the slope of this line is m equals 2/7. Next, I'm going to use point slope form to find a line for this equation using the slope that I just found and a single point. Here I can just use one of the points that I used to find the slope, so let's just use point 1, 17, 0. So point slope form is y minus y1 equals m times x minus x1. So for us, that's going to be y minus y1 is 0. And this is equal to m is 2 over 7 times the quantity x minus x1, which is 17. All right, I am going to distribute here. Y minus 0, I can just say this is y, equals 2/7 x minus, just multiply here, 2 times 17, that's going to give you 34. This will still be over 7. So the equation of this line, the equation of the model, the linear model that I'm going to use, is y equals 2/7 x minus 34/7. The problem, though, is that this is just an approximation. If I go back up to my data here, I used this line, and I kind of eyeballed that line. But what if I had a different line that was similar? What if I used a line like this? That would also be pretty close to my data. And what if I used a line like this? Okay, that would also be pretty close. In fact, there are a lot of different lines, an infinite number of lines I could use, and I just picked one line and used that as my linear model as an approximation. How do I know how well the line that I chose, the model that I chose, fits for the data that I have? Well, this is how we determine this. We can actually measure how close the model fits the data by comparing the actual values with the values given by the model. Here's what I mean by that. Do you remember we had someone that was 17 years old and owned 0 cars? They've owned 0 cars. Well, my model, if I look back at it, also shows that blue line that would also be 0. Okay, let's write down what that equation is again. That was y equals 2/7 x and then minus 34/7. This is the linear model that we found. And if I plug 17 into this, so 2/7 and then times 17 minus 34/7. There we go, 0. And let's look at 18. I had an 18-year-old that said that they owned 1 car. But according to my linear model, if I plug 18 into this, let's replace 17 here, then my linear model shows that an 18-year-old would own 0.2857. We'll say that's 0.286 cars in their lifetime. That's a difference of 0.714. If I take one and subtract the other, I'll get 0.714. Whereas before, the 17-year-old, that difference is 0, because 0 minus 0 is 0. Well, if I do this for every single point on my scatter plot, okay, that would be the next one would be a 20-year-old. I plug 20 into my model, and I say a 20-year-old would have about 0.857 cars, whereas my actual data shows 1 for a difference of 0.143. For a 21-year-old, my data shows that they've owned 2 cars, but my model would say 1.143 for a difference of 0.857. I find all of these differences and I square them. So 0 squared is 0. 0.714 squared is 0.510. 0.143 squared is 0.020. 0.857 squared is 0.734. And I do this for every single point. And once I'm done with that, I take all of my difference squared numbers and I add them together. The sum of the squared differences is 11.344. And the model that I find with the least sum, the smallest number here, this would be called the least squares regression line, and that would be the best fit. But remember that I just kind of eyeballed this line. And all of my data that I'm using for my linear model is based on this line and the equation I found for it. But I could have this green line, or this red line, or this other one. And in order to determine which is best, I would have to do this exact same process for every single one. And even then, I wouldn't necessarily know that I'd found the best one. I'd just know that I'd found the best one of the ones that I've tried. So is there a better way to do this? Well, luckily, we have a graphing calculator. Here I've got the TI-84 plus CE, the same one that we've got in class. And here are some steps to find a linear regression. First, I'm going to press the Stat button. That's going to be next to these arrows here, followed by 5, the Setup Editor, and then Enter. Okay, so now I'm done. Now, let's press Stat, and then Enter to enter the Edit. Okay, this will get us into the editor. If there's any data in here, let's say that previously I had a 5 here, a 6 here, a 9 here, whatever else, I can go to the top, highlight this L1, hit clear, and then now press down, and this entire column will clear. So that's how to get rid of something if you've got a whole bunch of stuff in there from someone else using the calculator. What I want to do is I want to enter the X data I've collected into the L1 list, and I want to enter the Y data that I've collected into the L2 list. Okay, so what that means is I want to go all the way back to here, and then enter 17 is the first age, and then 18, 20, and so forth. So take a moment and do that on your calculator. I'll do that here as well. So I've got 21, then 22, and then maybe I'll do this in groups. So this first grouping, cars owned, that would be 0, 1, 1, 2, and 1. Okay, then this group, I've got an age of 24, 25, 27, 28, and 29. And cars owned would be 2, 2, 3, 1, and 3. I like to do this in groups. That way I know that, if I'm doing 5 at a time, then this should line up after all 5. Okay, then 29, 29. 30, 30, 30. And cars owned is 3 there, 4 for the next one, 3, 4, and 4. All right, my last group. Ages are 32, 33, 36, 37, and 41. And the number of cars they've owned in their lifetime are 5, 3, 6, 5, and 7. Okay, so now I've got all of this data in my table here, my L1 and my L2. Let's go back to my instructions. When finished, press Stat. Here we are. And then the right arrow to go to Calc. And then I'm going to go to the 4th option to select Lin Reg AX plus B. This is a linear regression, and I'm going to be using the format AX plus B. Okay, everything here looks good. I'm using L1 for my X list, my L2 for my Y list. I'm going to go down to Calculate, and I hit Enter. Okay, according to this, the best model would have a slope of 0.2669. Let's write that down. According to this, I would have y equals 0.2669 9x plus b would be negative 4.461. So really we can just say minus 4.461. Now, how do I know how close my model was to this? Well, the model I had, if you recall, was y equals 2/7. Here it is again. Y equals 2/7 x minus 34/7. So let's compare. I'm going to clear this. 2/7 was the slope that my linear model came up with, and that's 0.2857. Pretty close to 0.2669. Not exact, but really close. So it appears my model was pretty good, but not quite the best. Okay, what about the intercept? What about b? I've got negative 34/7 is what I came up with, which is negative 4.857. Again, pretty close to negative 4.461, but not quite. So this is why we want to use a calculator, because this is going to be much more exact. And while I can get close, I can make a good estimate, we want to be as precise as possible. Lastly, to determine how well this line fits, to determine how well my data is correlated, I can actually have the calculator show that as well. I want to find a correlation coefficient. These are going to be R values. To find this, I'm going to hit second, go to catalog, and I'm going to go all the way down to diagnostic on. So go ahead and find that here. It's a little ways down. There it is, diagnostic on. Go ahead and hit enter, and enter again. So now it's done. And if I go back into stat, calc, go back down to linear regression, hit enter, and then calculate. Now I've got here R squared and R. This value varies between -1 and 1. And the closer the absolute value of R and R squared are to 1, the better the correlation of the data. So here I've got an R squared of 0.838 and an R of 0.9156. Pretty close. It appears the data is correlated. You'll have an assignment where you'll be using all of the tools that we showed you today and we talked about. If you have any questions, please let me know.